Hi, I'm Ben-Yaakov. This presentation is entitled The Muddle of Nonlinear Capacitor Measurement, or subtitled as How is the Capacitance Measured and What do the results mean? We find in datasheet of ceramic capacitor, in particular ferroelectric ceramic capacitor, class 2, like X7R or X5R, plots like this. Here we have the capacitance as a function of the DC bias, and it is done by exposing the capacitor to a bias, which is changing, and then an excitation, which is typically 0.5 volt, although some manufacturers do it with 1 volt or 0.1 volt, so it's not a fixed number or there's no standard about it. And then there is this type of a plot in which we have this is now AC excitation. It's 0 DC, like in this point. And then all of a sudden we have this hump here, and this is done by exposing the capacitor to an AC voltage only without a bias. So this is the kind of information that we find. However, it's very important to realize, and this is the point of this presentation, that these data are dependent on how they were measured. And you can measure a capacitor in a number of ways, and this is done by many researchers and manufacturers different ways, and each one of the ways, each one of the method might give you a plot which looks different. It's okay, but you have to make sure that you understand that it was taken by a certain method, different perhaps from another plot by another manufacturer that was measured by another method. So this is the point of this presentation. Now we find in some papers, for example in this conference paper, a figure like this in which they are showing their own measurement and the vendor data. Well, it is possible that there is an error here, but it is also possible and in fact likely that the difference here is due to the fact that these measurements were done by different methods. And if you do it by different method, you'll get different plots. So therefore, one has to be extremely careful when looking at data of ceramic capacitor, nonlinear ceramic capacitors. As an introduction to the subject, let me go back one step just to define what is capacitance. Okay? So capacitance is actually the ratio between the charge and voltage. This is the definition of capacitance. Now, a linear capacitor will have a relationship which is linear. A nonlinear capacitor has a nonlinear relationship between the charge and the voltage. This is due to the fact that the dielectric constant is affected by the electric field imposed on it. And as the voltage goes up, the electric field strength is increasing, and therefore the capacitance, in fact, is decreasing. Now, in the case of a nonlinear capacitor, we can actually define many types of capacitances, and I'm showing here 3 of the many possible. One is the differential of small signal capacitance. This will be the slope at a given point. Obviously, it's a function of the voltage. As the voltage is changing, the slope is also changing. So we have this differential small signal or incremental capacitance, which is the derivative here. And this is this definition here. Now we can also talk about the total capacitance, which is the total Q over the total V. And this will be the total capacitance defined by Q over V at any given point. This is also a function of the voltage. And then we can also define an AC capacitance, and that is when you are at a given DC bias, say, it could be 0 or any other one, and then there is a large amplitude here of AC, and this slope will be the capacitance, but the actual curve is of course different. So this will be the large signal capacitance. So there are at least here 3 capacitances, and there are some more. I'll talk about them a little bit later. So these plots are actually describing 2 different capacitances. Doesn't say here, but it should have. This should be called the differential capacitance, and this should be called the AC capacitor. This is measured by looking at the slope, small signal, 0.5 volt or less, here at any given DC bias. This is the DC bias here. And this one is around 0 with different amplitudes. Okay, the amplitude is changing, and then therefore the slope is changing, and therefore we get this different curve, which is something entirely different. It is important to know that even with a small excitation, say the 0.5 volt around the DC of 1 volt, the current of the capacitor will sort of look sinusoidal, but in fact it includes harmonics. Okay, this is the FFT of this signal, and you see we see here the first harmonic, and then we see, surprise, surprise, the second harmonic, and then the third harmonic, etc. So the point that I'm making is that you cannot tell by just looking at the waveform as to what is the harmonic contact of this signal. So when you look up at papers, research papers, data sheets, or application notes, etc., you find that there are many types of measurement methods that have been used or are being used to measure nonlinear capacitors. There is one group which is around the impedance. That is, the impedance is measured. But how do you measure the voltage and the current? You can measure the RMS, you can measure the first harmonics, or you can measure the peak-to-peak. All of them have been described in the literature. You can find that it was suggested or measured or applied in one way or another. And then there is another group, which is a charge to voltage, Q over V, and this is using actually RC circuits for charging and discharging a capacitor and looking at the curve of the charging. So this is like related to the charge. Now, the real physical capacitor includes a equivalent series resistance and equivalent series inductance. So things are getting more complicated because then it's not just a pure capacitor, but then it has some phase shift due to the inductance and the resistance. So you do have to look also at the phase, not just the amplitude. In this presentation, I'm just concentrating on the capacitor itself, although, of course, the issue of ESR and ESL are very important, but just for the sake of simplicity, I'm sort of concentrating here on this basic characteristic of the capacitor. So as I've said, there is a group of measurement which is based on impedance, okay? Now, the impedance of a capacitor is 1 over omega C, and then the impedance can be measured by voltage over current, and therefore you can get the capacitance as the current over omega, the voltage. But the question is, how do you measure the current and how do you measure the voltage? Well, usually the voltage is imposed like an AC source, sinusoidal. But still, if there is a resistor in series, then the voltage here will not be sinusoidal. So the question is, how do you measure these parameters, the current and the voltage? You can measure the RMS with a voltmeter, you might say, through RMS, of course. You can measure the peak-to-peak by scope. And then you can measure by first harmonic. Now, as a matter of fact, network analyzer and impedance analyzer are working this way. They are not looking at the RMS of the signal, but rather they are extracting the first harmonic. Now, if you have a signal which is highly distorted, obviously the first harmonic, well, it's a measure, but it's not the whole story. It is different from measuring the RMS. There are two different things. So when measuring a capacitor by a network analyzer, you look only at the first harmonics of these two signals, the current and the voltage. While with the RMS, you look at the total signal, including, of course, the harmonics as an RMS. So here is an example. This is actually taken from the paper that I've referenced earlier, in which a network analyzer was used to measure the nonlinear capacitor. And in this case, they found, as I've shown, that the measurement that they got is different from the vendor. And the question is, did the vendor use the same method? Same method in terms of the fact that this instrument is looking at the first harmonics and whether the excitation was exactly as the vendor did. So I don't know. Maybe it's a real difference here, and the conditions are exactly the same, but I would suspect that they are not. Now, what about the peak-to-peak approach? You can look at the current and the voltage on a scope and measure the peak-to-peak value or the peak value. Now, this is okay if the signal is small and there's practically no distortion, but if, of course, the magnitude of the excitation going up, you get a distortion, and obviously you'll get a number, no question about that, but it'll be different from the number you will get if you'll measure the RMS of the signal. So this is the point that I'm trying to emphasize here. And then there is another method which is based on, as I've said, actually charge, and this is done by having a oscillator which has two thresholds with this positive feedback, and then they are charging and discharging this test capacitor with bias and measuring the time it takes from one threshold while discharging the capacitor to the other threshold. Now, this time now is measured by a current source, which is charging a capacitor. So the average value of this signal here, of this triangle, is basically related to the time. The longer the time, the more you'll have here, the higher will be, of course, the value here. And then filtering it out, you can get a signal which is proportional to the time, and then you can work it out from this time back to what is this capacitance. But the point is that this capacitance is an entirely different from the RMS capacitor that we talked about in the case of a nonlinear capacitor. Well, if the capacitor is linear, of course, all these will be the same, or if the signal is very small. Here, you cannot have a small signal. It's not practical, okay? So, again, there are many methods. Each one of them is valid, but comparison between them is not trivial. And here are some plots from the write-up of analog devices of this method of measurement. We see here the discharge of the capacitor. This is the time, the relevant time, and this time now is measured by charging a capacitor to a given value, and of course, for a different capacitor, the time will be different, and you'll get to a higher value if the time is longer, and from this you can work out back to what is the value of this equivalent capacitance. So I'm going to demonstrate now by simulation this issue of the different method, and for that we need a model, and the model that I'm using, and this is taken from one of the videos in my YouTube channel on capacitors, you can find it there, and I'm going to use this model here, that the current is CD, this is the differential capacitance, which is the function of voltage, dV/dt, okay? So this is the model that I'm using in this simulation that I'm going to show. Now, the simulation is done by having a current-dependent source, which is defined by this equation. dV/dt is done by this operator of LT-spice. This is an LT-spice simulation. ddt is the derivative of the voltage between A and B, here A and B. Now, we have a problem here in that simulators do not recognize just a variable as a function of voltage. You have to code it or emulate it by a voltage or a current that the simulator recognizes. So therefore, what we are doing is that we are creating a voltage which is numerically equal to this capacitance, and this is done by a table. So for each value of voltage across the capacitor, the table will give out a voltage which is numerically equal to the differential capacitor. So this is very well known, and again, it is shown in some of my YouTube videos. Now, combining these two plots, I've created a table which has a finer definition than the 0.5 volt, especially at the beginning here. Because as it turns out, you can use this plot to go back to this plot. Now, this is a long story, just too long for this video. I don't want to make it just too long. And therefore, hopefully will present a video that will just explain how was this done, creating a higher resolution plot for the derivative capacitor, CD, in this region here, which is related to this plot here. And here is the LT-SPICE simulation model. Let's start with the table. We have here a table. Again, it includes the first part, the high resolution, and the later part here. Now, what happens here is that this table looks at the voltage across the capacitor. This is now the dependent current source. This is the capacitor. So this is the voltage here. Here it is. And providing a value for the differential capacitor for any given voltage across this capacitor. Okay? And so this voltage will appear here. And then we use it in the definition of the variable capacitor, the current dependent source. And here is this value, this is the capacitance, and this is the derivative of the voltage across the capacitance according to the model. Now, this then creates a current. I can take the integral of the current to get the charge. SDT is the operator of LT-SPICE of integration. And then I can do some other calculation, which I'm, again, due to lack of time, not going into deep into them, but just to say the following. Using this information, I can create a value for the capacitance as if it's measured by the RMS, because I have all this information, as if it was measured by peak to peak, or the first harmonic, or by this RC or charge type of a measurement. Okay, so I can create these values from the actual run of this simulation. So here is one example. This is now the small signal CD capacitance of this capacitor. This is from the datasheet, and this is what I'm getting from the simulation for all the four type of capacitors. This is the peak-to-peak, this is the charge type or RC, this is the RMS, and this is the first harmonic. You see that for the small signal, most of these capacitances are the same, should be the same, because in small signal there is no appreciable distortion, except for the peak-to-peak. This is this delta here, which shows a difference because the relationship between the peak value and the RMS is really changing very quickly in a nonlinear capacitor. The other ones are pretty close, and as you can see, the simulation is really reproducing very nicely this plot here, from which, of course, the data was taken to create the table. But again, it was taken from this and also from the AC plot. Now, in the datasheet, the measurement was supposedly done with the 0.5 volt RMS, should be volt here. Now, if I'm running it now in the simulation with a test signal of 1 volt RMS, you see that I'm getting something different. You see at the very beginning, it's sort of smearing it out. Here it's like approaching 10 microfarad, and here it's like almost 9. So you see that the magnitude makes a big difference in the behavior of this plot. So if one vendor or one manufacturer is measuring the capacitor with 0.1, the other one with 1 volt, you cannot compare the two. Well, you can compare, but you have to realize that these are not the same capacitances. And having this high resolution model, I can now run it with a very fine excitation of 0.1 volt peak only, rather than the 0.5. This is the RMS, but this is 0.1 volt. So it's very fine resolution. And what we see here is that the CD is really changing quite a bit at the around zero. This is a double-sided now simulation just to show that the plus and minus are behaving. Plus and minus voltages are providing the same results, of course. And you see that you see this hump here, and then you have this drop. So again, the magnitude of this excitation is very, very important, and you get different results. Now, when the resolution is that fine, all the capacitances are, of course, the same because there is practically no distortion here, and therefore they should be the same. However, if I look at the AC capacitance around 0 volt DC, I see quite a bit of a difference between all these capacitances. Now, the RMS and the first harmonic are just about the same. It's very interesting that the first harmonic and the RMS are not that much different, but the peak-to-peak is quite a bit different, and the RC is entirely different. I don't understand what's going on here, but let's leave it alone now and just concentrate on this. Now, if I zoom at this curve here, this RMS and the first harmonics, here it is. This is the RMS and this is the first harmonic, and compare it to the datasheet, you'd see that I'm getting exactly the same thing. So this is now AC excitation, no DC, and the difference between these two is that this is representing the RMS capacitance, and this is the first harmonic capacitance, as you would measure, say, with a network analyzer. If, however, I'm looking at this AC capacitance with some DC bias, you see a big difference now. Now, this delta, the peak-to-peak, is now shooting up for this range here, while the RMS is now going down. So, again, the method of measurement makes a very big difference whenever you start to have distortion in the signals. So what are the conclusions of this presentation? That there are many different ways to measure the capacitance of a nonlinear capacitor. It is important to cite the method of measurement when reporting the data. So it's very important to give all the information, including the excitation, the DC, and the method of measuring the voltage and the current. Is it RMS? Is it the peak value? Or is it the first harmonic? Or is it by RC? And then one should be very careful when comparing capacitance values that were obtained by different measurement methods. If the methods are different, you may get plots which look different. Okay, it doesn't mean that there is an error, but it just the method of measurement was different. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.